Welcome to the lesson on the overview of programming. Upon completion of this lesson, learners will be able to explain the key programming concepts such as variables, control structures, operators, flowcharts, and input-output functions. To start off, let's look at the key software features that enable effective robot programming and control. Robotic controllers are programmed using several key software features such as variables, control structures, operators, flowcharts, and input-output functions. We will discuss each of these components in detail to understand how they work together in robotic control programming. To begin with, variables are named storage locations in a program that hold data values that can change during program execution. These variables are stored in the memory with specific designated addresses, allowing the program to access and modify them as needed. They can be of different types, depending on the operations being performed on them, such as integers for counting, floating point numbers for calculations, or strings for text data. Each variable type has a fixed size allotted in the system memory, determined by the data type and the system architecture. This ensures efficient memory management and proper data handling during program execution. Primitive data types include Boolean values, which represent true-false conditions like is robot active equal true or has error equal false, and numeric types, which consists of both characters like A, B, 1, $, and integral values. Integral values further break down into integers such as -5, 0, 42, 1000, and floats like 3.14, -0.001, and 98.6. Non-primitive data types include strings, which can store text data like hello world, robot_001, or temperature 25 degrees Celsius, and arrays that can hold collections of values such as 1, 2, 3, 4, 5, red, green, blue, or true, false, true. Each of these data types serves specific purposes in programming, allowing for efficient storage and manipulation of different kinds of information. Next, let's talk about control structures. Control structures are essentially blocks of code with well-defined structures that enable us to make decisions and execute specific parts of our program based on given conditions. These essential programming elements allow programs to run multiple lines of code based on assigned conditions, providing flexibility and decision-making capability in program execution. Control structures can be embedded into function blocks and used for complex logical operations, as illustrated in the flowchart where an if statement evaluates condition A and executes either path B when true or path C when false. This type of structure allows for dynamic, condition-based program flow rather than just sequential execution. For example, an if statement allows us to say, if this condition is met, do this. Similarly, an if-else statement lets us specify, if this condition is met, do this, otherwise do something else. There are other common structures as well. For example, for loops let us repeat a task a specific number of times or until a certain condition is met, while loops execute a block of code as long as a condition remains true. Switch statements handle multiple possible values for a variable and execute corresponding code blocks based on the value. For example, if the value is 0, do this. If it's 2, do something else, etc. These structures allow us to build programs that perform actions based on different scenarios, much like how we might react to seeing a light turn on, deciding what to do depending on what it means. For example, if a program detects certain input or receives a flag indicating a specific event, it can follow predefined instructions accordingly. Although the syntax for these structures may differ slightly between programming languages, as shown in the second column of the table, their core functionality, if statements, for loops, while loops, and switch statements, remains consistent across most programming languages. Let's cover a few more control structures. For example, the do-while loop is like the while loop in that it continues executing as long as a specific condition is met. However, the key difference is that the do-while loop always executes the code block at least once, even if the condition is false from the start. We also have structures like break, continue, and return, which allow us to control the flow of a program by stopping or skipping specific parts of code. For example, a break is often used to prematurely exit a loop or a switch statement. Continue skips the rest of the current iteration in a loop and moves to the next iteration. Return exits a function entirely and optionally sends a value back to the calling function. Additionally, there's goto, which enables jumping to a specific point in the code. While powerful, goto is generally discouraged because it can make the code harder to read and debug. These control structures can be combined or nested for more complex functionality. For example, a break statement is frequently nested inside a switch statement to instruct the program to stop evaluating further cases after executing a specific one. For example, if the program handles a case for the value 2, a break tells the program to skip the remaining cases, for example 3 through x. This lets us define precise actions and exit conditions for our program, such as stopping execution at a specific point or jumping to a new section of code to evaluate another condition. Finally, one crucial aspect of implementing control structures is syntax. A compiler is designed to recognize only the syntax of its respective programming language. For example, a for loop written in C must strictly follow the syntax rules of C. If you attempt to use a Python or Java-style loop in a C program, the compiler won't understand it. Thus, adhering to the syntax of the language you are working with is essential for proper code execution. Now that we've covered variables and control structures, let's look at operators. Operators are symbols or keywords used to perform specific operations, such as arithmetic calculations, comparisons, or logical evaluations. Essentially, they are the building blocks that allow us to manipulate data and make decisions within our programs. There are three primary types of operators: arithmetic, comparison, and Boolean. Let us look into these in greater detail. Arithmetic operators are used for mathematical operations like addition, subtraction, multiplication, division, and modulus or remainder. For example, the plus symbol for addition, the minus symbol for subtraction, the asterisk symbol for multiplication, the slash symbol for division, and the percentage symbol for modulus. Comparison operators allow us to compare two values and return a Boolean result, true or false. For example, the greater than symbol checks if one value is greater than another, the less than symbol checks if one value is less than another, the greater than or equal to symbol, and the less than or equal to symbol checks for greater than or equal to, or less than or equal to, respectively, the not equal to symbol checks for inequality. Boolean or logical operators operate on binary values, true, false, and often replicate the behavior of digital logic gates. Common Boolean operators include the symbol AND, which returns true if both conditions are true, the OR returns true if at least one condition is true, the NOT symbol inverts the truth value. XOR symbol in some languages returns true if exactly one of the conditions is true. Each of these operator types is essential for building functional programs, enabling everything from basic calculations to complex decision-making. The symbols and usage of operators can vary between programming languages. For example, arithmetic operators are generally consistent across languages. Some languages, like C, offer shorthand operators such as plus plus for incrementing a value by 1 or minus minus for decrementing, whereas Python does not support these. Boolean operators can also differ. For example, C uses the double ampersand symbols for AND, while Python uses the keyword AND. As with control structures, understanding the syntax and conventions of the specific programming language you are using is critical to correctly implementing operators. Next, let's talk about flowcharts. Flowcharts are visual representations that diagram the sequence of steps, decisions, and operations within a process or algorithm. While programming languages execute in a linear flow path, they can incorporate multiple conditions and iterations within a single program. The process begins with a specific task and continues execution until that task is completed, following the paths and decision points laid out in the flowchart. This visual tool helps programmers understand complex logic flows before writing actual code, making it easier to identify potential issues and optimize program structure. When building flowcharts, it's helpful to use a standardized set of symbols to represent different actions, processes, and decisions within the algorithm. The following chart outlines some of the most common symbols and their meanings. The terminal symbol, represented by an oval or rounded rectangle, marks either the beginning or end of a program, process, or interrupt program. It clearly indicates where the flow starts and terminates. The process symbol, shown as a regular rectangle, represents any internal operation that occurs within the processor or memory. This could include calculations, data manipulations, or any other internal computing operations. The input-output symbol, depicted as a parallelogram, is used to represent any data movement into or out of the system. This symbol indicates operations where the computer either receives input data or produces results as output, such as reading sensor data or displaying information. The decision symbol, typically a diamond shape, is used for conditional branching in programs. It represents points where a binary decision must be made, questions that can only be answered with yes, no, or true, false, determining which path the program will follow. The predefined process symbol represents a set of operations that are already defined elsewhere. It's used when calling subroutines or interrupt programs, allowing for modular program design and code reuse. The connector symbol serves a practical purpose in flowchart drawing. It helps maintain clarity by avoiding line intersections and reverse flows. It's particularly useful when connecting parts of a flowchart that would otherwise be difficult to link directly. Flow lines, typically arrows, are fundamental elements that show the direction of program execution, indicating the sequence in which operations are performed. All these symbols form the flowchart elements needed to visually represent any program's logic and flow. Now that we've covered variables, control structures, operators, and flowcharts, let's add one more important piece to the puzzle, namely input and output functions. These are essential components that handle data flow between the program and external devices or systems, allowing computer algorithms to communicate effectively with the external world to receive and send useful information. Input functions consists of various ways of receiving data, including reading sensor data like temperature, pressure, and position, accepting user commands, scanning barcodes or radio frequency identification, abbreviated as RFID tags, reading files or database entries, receiving network signals, and getting keyboard or mouse inputs. On the output side, functions include controlling actuators or motors, displaying information on screens, sending signals to other devices, writing data to files, generating reports, and triggering alarms or notifications. This two-way communication system forms the backbone of how programs interact with their environment, making it possible to create responsive and interactive systems. Listed here are some examples to show how input-output functions play vital roles in robotic applications in EV manufacturing. A robotic arm uses input functions to constantly read position sensors, determining its exact location and orientation, while output functions control its servo motors to achieve precise movements and manipulations. In assembly lines, robots employ input functions to scan incoming parts using barcode readers or vision systems, while output functions control conveyor speeds and direct part routing. Automated guided vehicles rely on input functions to read navigation signals from floor markers or beacons, while output functions control their drive systems and display their status. Quality control systems demonstrate complex I/O integration by using input functions to gather data from various inspection sensors such as visual, dimensional, weight, and output functions to generate detailed quality reports and trigger sorting mechanisms for defective products. In summary, programming concepts consist of several key elements: variables that store different types of data in memory for program use, operators that perform calculations and comparisons between variables, and control structures that enable program decision-making through conditional code execution. Flowcharts visually represent program logic using standard symbols, while I/O functions allow programs to communicate with external devices and users. Together, these elements form the foundation of effective program design and implementation. Thank you.